At 9 a.m. on the morning of October 1st, 1933, construction began on Norris Dam. The site was a gorge on the Clinch River in Upper East Tennessee, in a county where 30% of the population had malaria, where average farm income was under $200 a year, and where the river that would be dammed rose every spring and took the topsoil when it went. The men who showed up that morning were Depression-era labor. Some of them former sharecroppers, some former mine workers, most of them from within 30 miles of the gorge. They came because the pay was real and the work was immediate. What they were beginning was not a dam. They were beginning the construction program that would build 21 dams across a 7-state watershed and transform the Tennessee River from an unnavigated seasonal hazard into a 650-mile navigable highway, and deliver electricity to a region that in 1933 had almost none. The Tennessee Valley Authority Act had been signed by President Roosevelt on May 18, 1933, 135 days before the first concrete was poured. The legislation was drafted, passed, and signed in a period when a president who had been in office for 11 weeks was attempting to rebuild an economy in free fall. Speed was the political requirement. What the speed produced at the construction site was an undertaking of a kind that had never been attempted before. Multiple large concrete dams being built simultaneously across an interconnected river system under a single coordinating organization that was, as of October 1st, still hiring its engineers. Norris Dam would be 1,860 feet long, 265 feet high, and 208 feet thick at its base. It would require 1,02,300 cubic yards of concrete. Its gates would close on March 4th, 1936, 2 years, 5 months, and 3 days after that first morning in the gorge. The men who showed up on October 1st, 1933, did not know any of this yet. They knew there was work. The Tennessee Valley in 1933 was not poor in the way that cities are poor. It was poor in the way that land is poor when it has been used past its capacity for a century, and when the river that runs through it cannot be controlled. Spring flooding was the defining rhythm of life in the Tennessee Valley. Each year, the snowmelt from the Appalachian headwaters, combined with spring rainfall across a watershed that spanned 7 states and 40,000 square miles, sent the Tennessee River over its banks. Chattanooga had flooded seriously in 1867, 1875, 1886, and 1917. When the river came up, it took topsoil, it took crops. Sometimes it took animals and structures. What it left behind was depleted ground that had to be put back into cultivation before the next growing season. On farms that had no electricity, no indoor plumbing in 92% of cases, no connection to a power grid that would have allowed machinery to substitute for the seasonal flood damage. 30% of the population was affected by malaria. The average per capita income was 44% of the national average. In Union County, Tennessee, the county directly in the path of the Norris Reservoir, there were no electrical utilities at all in 1926. Before we go further, if this kind of story matters to you, consider subscribing to the channel. Every video here is built around the systems that actually moved America. The construction programs, the power infrastructure, the engineering decisions that most people never think about until they see what the landscape looked like before. Before TVA, 30% of the people in this valley had malaria. Almost none had electricity. And the river flooded their farms every spring. And TVA changed all 3 of those things in less than a decade. Did you or someone in your family work on a TVA dam project in the 1930s or 1940s, At Norris, Wheeler, Chickamauga, or any other site across the valley? What trade did they work? And were they ever in the town of Norris? The concrete techniques, TVA, developed at Norris and Wheeler became standard practice for mass concrete dam construction for the next 30 years. And this channel intends to follow that story. Now, back to the valley. The TVA's engineering program was not assembled in advance. It was assembled as the money arrived and the organization formed. The Unified Development of the Tennessee River System Plan was not approved until March 1936, 2.5 years after the first ground was broken at Norris. In the intervening period, TVA was building what it could with the funds Congress had appropriated, relying heavily on Army Corps of Engineers and Bureau of Reclamation designs and personnel, while simultaneously developing its own engineering capacity. What TVA ultimately proposed was a staircase. The Tennessee River drops from the Appalachian headwaters in Virginia and North Carolina through a long series of gorges and valleys to its confluence with the Ohio River in western Kentucky. A system of dams placed at intervals across the main stem and on the major tributaries would transform that staircase of uncontrolled falls and floods into a series of navigable pools, each one connected to the next by a navigation lock. 9 dams on the main stem alone. Additional dams on the Clinch, the Hiwassee, the Little Tennessee, and other tributaries. Each dam a massive concrete structure, each one incorporating a powerhouse, each one requiring the construction of a new road network, the acquisition of land measured in hundreds of thousands of acres, and the relocation of the families who had farmed that land. The engineering challenge was not any individual dam. Any single dam on the list was within the capability of the Army Corps or Bureau of Reclamation to design and build. The challenge was doing all of them at the same time, with a common design standard under a common management structure, coordinating the movement of concrete, steel, turbine components, and labor across a watershed that stretched more than 600 miles from one end to the other. Nothing like this had been attempted in American civil engineering before. The Tennessee Valley Authority built in concrete. Not a little concrete, more than 1 million cubic yards of concrete at Norris Dam alone, placed over 2.5 years in a mountain gorge 60 miles from the nearest large city. Concrete in a dam is not the same material as concrete in a building or a road. In a road, the concrete section is thin and the concrete cures without significant heat problems. In a gravity dam, the sections are massive. Some of the individual monolith blocks at Norris Dam were tens of feet wide and 20 to 30 feet tall. And the hydration of cement in that volume generates enough heat to crack the concrete from within as the mass cools unevenly. The Bureau of Reclamation had faced this problem at Hoover Dam, and TVA engineers studied and refined those solutions. The answer involved controlling the concrete mix, carefully specifying the cement content, the aggregate size, the water-to-cement ratio, and managing the temperature of the pour through pre-cooling of the mixing water and, at some sites, circulating cool water through pipes embedded in the concrete during curing. The mixing plant at Norris was a central operation rather than a collection of hand-mixed batches. Aggregate from nearby quarries was sized, washed, and separated into fractions. Cement arrived by rail, water was drawn and measured, and the mixture was produced in batches timed to the demand of the forms being filled at the face of the dam. Trucks, a fleet of them, carried the concrete from the mixing plant to the forms, east where it was placed by bucket and vibrated to consolidate. Over 1,002,300 cubic yards of concrete went into Norris Dam in 2.5 years. At Wheeler Dam, begun simultaneously, the volume was larger still. This was not just dam building. It was the industrialization of concrete placement at a scale that had only one precedent in American history. The Hoover Dam, which had been completed 2 years before. A concrete gravity dam is built in the riverbed. The river has to be somewhere else while that happens. The Cofferdam is the temporary structure that makes this possible. At every TVA dam site, before a single cubic yard of permanent concrete was poured, the river had to be diverted around the construction area through a series of upstream and downstream cofferdams, earth and rock-fill embankments sealed with clay cores, and through diversion tunnels or channels cut through the valley walls. At Norris, the Clinch River was diverted through a tunnel in the left valley wall, while the east half of the riverbed was dried out and the first concrete was placed. The process then reversed. The completed east portion of the dam served as its own cofferdam, while the tunnel flow was cut and the remaining riverbed excavated and poured. The cofferdam is inherently temporary. It is designed to hold the river out for the duration of construction, and it is designed to be removable or to be overwhelmed when the dam is complete. But a cofferdam that fails prematurely, that is overtopped by a flood event during construction, can destroy months of work, inundate the construction area, damage or destroy equipment, and kill workers in the zones below. Managing the risk of cofferdam failure required predicting the river's seasonal behavior over the construction period and designing the cofferdam height to match. TVA's engineers studied flood records on the Clinch, the Tennessee main stem, and the tributaries, and designed each cofferdam sequence to provide adequate freeboard above the expected design flood for the construction period. What made TVA's situation unusual was that the decisions at one dam site affected the flood probabilities at every other site downstream. A dam under construction upstream changed the hydrograph at every site below it. The program had to manage the river as a system, not as a collection of individual projects. In June 1934, 8 months after ground was broken at Norris Dam and Wheeler Dam, the Tennessee Valley Authority employed 9,173 people. By 1935, that number had risen to 16,000. By 1936, 5 dams were simultaneously under construction. The labor force that built the TVA system was drawn primarily from the Tennessee Valley itself, men who had been farming eroded land at subsistence income levels. Men who had worked in the coal and iron industries of the region and found those industries in Depression-era collapse. They came to dam construction with varying skills and physical conditions, and TVA's workforce management had to accommodate the full range. The approach TVA took at Norris was unprecedented for a federal construction project of the era. The town of Norris, Tennessee, was designed and built as a planned community to house construction workers and their families. It included 309 permanent houses designed to reflect regional architectural styles, 8 dormitories, a 544-seat cafeteria, a school for 400 pupils, a vocational training building, a 4,000-volume library, a store, a gas station, tennis and volleyball courts, and baseball diamonds. The town was not without its contradictions. TVA officials did not permit black workers and their families to live in Norris, claiming adherence to local racial customs in a region where black and white workers had, in fact, often shared the same work and the same communities for generations. Black workers on the project were housed in separate facilities. The decision was contested by black community leaders at the time, and historians have documented it as one of TVA's most significant institutional failures. At its peak, over 5,000 workers contributed to Norris Dam's construction, with 2,750 employed at a single point. Visitors came from across the country and around the world. Le Corbusier, Jean-Paul Sartre, Jesse Owens, Jawaharlal Nehru, and Eleanor Roosevelt all visited the dam during or after construction. The workers they came to see were almost entirely local. They were doing work that had never existed in their counties before. The construction of Norris Dam required the acquisition of more than 152,000 acres of land. It required the relocation of 2,841 families. It required the exhumation and reburial of 5,226 people. The town of Lewiston, 20 miles upstream from the dam, was inundated entirely. Communities across the Clinch River Valley, farms, churches, schools, mills, cemeteries, were acquired by eminent domain, cleared, and submerged. The families who had farmed that land, some for generations, received compensation determined by federal appraisers and were given a date by which they had to be out. The scale of the displacement across the entire TVA program was larger still. By 1946, TVA had acquired approximately 1.1 million acres across the 7-state watershed. Estimates of total population displacement vary between 72,000 and 125,000 people, roughly 15,000 families, depending on the source and methodology. The variation reflects the difficulty of tracking a population that was, in many cases, dispersed into surrounding counties without formal resettlement programs. TVA's handling of the displacement was not uniformly poor. Some families received land in exchange for land. Some received relocation assistance. Some entered the TVA workforce and stayed in the region. But the compensation was not equal across racial lines. Black families received less than white families for equivalent properties. And the disruption to community networks, to extended family arrangements, to the informal economies of rural mountain communities, was not captured in any compensation schedule. Decades later, many of those displaced would acknowledge that their material conditions had improved after relocation. The land they had farmed was often marginal. The economies they entered were, in many cases, better than the one they left. What the displacement cost them in terms of place, community, and belonging was not something that any economic outcome measure could capture, and no TVA report attempted to. A dam without turbines is a flood control structure. The reason TVA built dams was to generate electricity, and generating electricity in a hydroelectric powerhouse required the installation of machinery of a scale and precision that posed its own set of construction and logistics challenges, entirely separate from those of the dam itself. Each generating unit at a TVA dam consisted of a hydraulic turbine and a generator. The turbine sat at the base of the powerhouse, directly in the water passage. The penstock that directed the flow of water from the reservoir through the dam structure. Water pressure drove the turbine runner, a precisely machined wheel of cast iron or steel whose blade geometry was engineered to extract maximum energy from the available head pressure and flow rate. The runner connected via a vertical shaft to the generator above, where the rotating electromagnetic field produced the alternating current that would travel through the transmission system to the region's homes and industries. The turbine components were manufactured at facilities in Pennsylvania, Ohio, and elsewhere in the industrial Midwest. They arrived at the dam site by rail, transferred to heavy trucks for the final overland leg, and moved into position by the powerhouse cranes. Overhead traveling cranes of substantial capacity built into the powerhouse structure itself. The precision required for turbine installation exceeded anything else on the construction site. The bearing surfaces, the shaft alignment, the clearances between runner blades and the turbine housing, all were held to tolerances measured in thousandths of an inch, in a structure that had just been built from millions of cubic yards of concrete that was still curing. The alignment procedure could take weeks. A turbine misaligned on installation would vibrate at speed, damage the bearings, and require disassembly. The first generator at Norris Dam went online on July 28, 1936. 4 months after the gates closed, the dam was producing power. When the United States entered the Second World War in December 1941, the Tennessee Valley Authority was 9 years old and had been building dams continuously since October 1933. The war did not slow the program, it accelerated it. The demand driver was aluminum. Producing aluminum requires extraordinary quantities of electricity, approximately 7 kilowatt-hours per pound of aluminum produced. Aluminum was the structural material of military aircraft, and the United States was building aircraft as fast as its industrial base could sustain. The production plants, at Alcoa in Tennessee, at Reynolds Metals in Alabama, needed more power than the TVA grid could currently supply. Between 1942 and 1945, TVA completed or accelerated the construction of multiple dams. The Cherokee Dam on the Holston River was built in 16 months, a speed that required the use of 3 work shifts around the clock and a labor force maintained at extraordinary levels despite wartime competition for workers from defense industries elsewhere. Douglas Dam on the French Broad River was completed in just under 12 months. The dam that powered Oak Ridge was not on a list that TVA could discuss publicly. Oak Ridge, in the hills of East Tennessee 40 miles from Knoxville, was the site of a uranium enrichment facility whose function was classified until the atomic bomb was used in August 1945. The electrical load of the uranium enrichment process at Oak Ridge was enormous, and that power came from the TVA grid, from the dams on the Clinch and the Tennessee and the tributaries that had been under construction since October 1st, 1933. The dams that the men broke ground on as a Depression employment program ended the war as the power source for the Manhattan Project. By 1946, the Tennessee Valley Authority had spent more than $2 billion in the Tennessee Valley and transformed a watershed across 7 states. Per capita income in the region, which had stood at 44% of the national average in 1933, had risen to 61% by 1953. Malaria had been virtually eliminated. The river that had flooded Chattanooga 6 times in the previous century had been brought under control by a staircase of concrete dams and reservoirs that absorbed the spring flood pulse before it could move downstream. The technical legacy of the TVA construction program extended well beyond the valley. The mass concrete methods TVA developed at Norris and Wheeler, the controlled mix designs, the thermal management procedures, marked the Cofferdam sequencing for multi-site programs, were adopted by the Army Corps of Engineers and the Bureau of Reclamation as standard practice. They were applied to the post-war wave of dam building across the American West, and they were transferred through American foreign assistance programs to infrastructure projects in South Asia, Africa, and Latin America. David Lilienthal, TVA's director, wrote a book calling the TVA model a blueprint for development worldwide. President Truman cited it in his Point 4 program for technical assistance to developing nations. The chief architect who gave the dams their modernist identity, Roland Wank, produced a body of work in concrete and glass and landscape design that is only now receiving the formal architectural recognition it deserves. The powerhouses at Norris, Wheeler, and Chickamauga are recognized structures on the National Register of Historic Places. What the system cost, in the displacement of 72,000 to 125,000 people, in the loss of communities that had existed for generations, in the racial inequities of how the program was administered, was not captured in any of the program's official measures of success. The river was controlled. The lights came on. The families who lost their land and their communities often improved their material conditions and sometimes could not reconcile that improvement with what they had lost. That is what a program at this scale always costs. Whether the cost was worth it is not a question that engineering statistics answer. If this story gave you a clearer picture of what held these systems together and what it took when they came under pressure, subscribe to the channel. There are more programs, more dams, more construction decisions, and more displaced communities still to document. The concrete placement and cooling techniques TVA developed at Norris and Wheeler became standard practice for mass concrete dam construction for the next 30 years. And this channel intends to follow that transfer of method from Appalachia to the American West, and eventually to the post-war world. And if you have a connection to this kind of work, a relative who worked a TVA dam site, a family that was displaced by a reservoir, someone who grew up in the town of Norris or in a farm that went under the water, tell us in the comments. What dam were they near? What trade did they work? What did they say about the valley before and after? The most complete record of how these systems were built and run isn't in any report. It's in the people who were actually there.